So I want to talk today about, main point is the need that we have for math, that we really do need to be proving the security of our systems. We're building lots of different consensus systems, but we really do need to get down to proving the security. Asynchronous Byzantine is kind of the highest level, but there's various ways that you could prove things that are less than that. And I think that the analysis is important, and I've loved seeing some of the analysis that we've been going on the last 2 days. This has been a great conference. I've really enjoyed it. So what I'm going to do is talk just briefly about what is this Byzantine thing. Lots of the speakers have mentioned it and talked about it, but maybe not everybody is familiar with it. It's kind of important. So we should talk about that. And then the question is, well, could you actually achieve that in a fast system? Well, let me give you an example. The system we have is Hashgraph. It is extremely fast, hundreds of thousands of transactions a second with sub-second latency. It's really fast, but it is asynchronous Byzantine. And so I'm just going to give that to you as an example of one that you may find interesting. That it is possible to have a rigorous math proof that something's asynchronous Byzantine when it's also practical, and that you can implement it and it runs very fast. And I don't know what you find entertaining, but I kind of enjoy case studies. If someone developed an algorithm, I'm kind of curious, what were the attacks you were thinking about? And so maybe you'll be entertained. I'm just going to talk about some of the attacks that I kind of had in my mind while I was working on Hashgraph and developing that. And it's kind of fun just to think about attacks. We've heard of lots of attacks over the last 2 days. So I'm going to give a case study of that. Hopefully it's entertaining. But the main message I want to say is just that, what we need to do is get down to do the math. What is this Byzantine? When we say that something is Byzantine fault tolerance, this goes back decades. What we are saying is that we're trying to get consensus on something, either a yes-no question or, in this conference, the ordering of transactions. And typically, we're going to start with talking about just a single shard, so it's a replicated state machine. Every node, every full node needs to get every transaction, and we want to come to an agreement on what the order is. The simpler forms are we're going to come to agreement on a yes-no question. That's the original form we talk about with Byzantine. And what does it mean? It means that we will come to consensus, guaranteed with probability 1. FLP says we have to be non-deterministic. So with probability 1, we will get consensus. And we'll know when we have consensus. It's not like each confirmation makes me a little bit more sure and that just keeps continuing. No, to be Byzantine, there has to be a moment when I say, I have consensus. And I have to never be wrong. So this is what Byzantine fault tolerant means. It means that I know I'll reach consensus, I know it's right, when I reach it, I know I've reached it, and I'm never wrong. And there's also, it has to not be a trivial solution, but that's a last condition. But that's what it means. Now to prove that, we have to assume something. For example, we have to assume that less than a third of our nodes are bad. And we assume that an attacker controls the internet. These are reasonable assumptions. They're very nice assumptions. You might want to make that 1/3 be a higher number, and there's a theorem that says you can't. A third's the best you'll ever achieve. No system can ever do better. So we have to make those assumptions when we're doing a BFT proof. But we also have to say, what do we mean by the attacker controls the internet? Do they have any limits on what they can do? Clearly, I have to say something like, well, if Alice keeps sending messages to Bob, eventually one will get through. We have to assume that. But do we have to make any assumptions about the timing? If we don't make any assumptions about the timing, and we still get this proof, we call that asynchronous BFT. It's asynchronous Byzantine when we don't make any assumptions about timing over the internet. Now, if we start making assumptions, then it's only partially asynchronous. That's not quite as good. So what kind of assumptions might you make? A lot of people will prove that something is asynchronous Byzantine by making the assumption, when Alice sends Bob a message, it always gets there within 10 seconds. Well, that's a pretty reasonable assumption, right? Or maybe we assume it gets there within X seconds for some constant X that we don't know, but it exists. Well, that's not a very terrible assumption, right? But wait a second. What if there is a botnet doing a distributed denial of service attack on Bob? What if somebody has compromised lots of little computers around the world, DVRs and web cameras and printers and baby monitors, and they've compromised all these little computers and programmed them all to flood Bob with packets so that Bob is shut down so that Bob can't get Alice's message. Even though Alice and Bob are honest, Alice's message doesn't get to Bob in 10 seconds or 100 seconds or as long as this attack is going on. We violated the assumption. So this is the difference between partially asynchronous and asynchronous. Or to put it another way, if you have a proof of partially asynchronous Byzantine fault tolerance, basically your proof starts off in the first line, assume there are no botnets in the world. Assume DDoS will never happen. And then at the end, you prove it's Byzantine. Whereas in asynchronous Byzantine, you start off your proof by saying, I won't make any assumptions. Maybe the world does have botnets. And then you prove Byzantine. What I would propose is that we really do need to get proofs of how secure our systems are. I think that we're getting to the point where we actually need to start doing proofs. If you can prove asynchronous Byzantine, that's great. You should do that. If we have a system, though, where we can't prove that, we have to prove something less, I would suggest that let's not prove partially asynchronous Byzantine. Let's prove asynchronous partially Byzantine. If we have to compromise on something, let's compromise on the conclusion, not on the assumptions. Because what tells us more? Do we learn more from a theorem that says, I am totally safe in a world that isn't the world we're in? That doesn't tell me anything. Or is it better to have a theorem that says, well, I'm somewhat safe, and here's exactly how safe I am in the world we actually live in? I think that tells us more. And so what I would propose is that we need to have theorems, actual math theorems, worked out in all the details, defining all the details, that prove asynchronous Byzantine if we can. But if we can't do that, then let's settle for reducing the Byzantine half, not reducing the asynchronous half. Okay, so that's kind of my takeaway message for today. But is that possible? Can we actually have asynchronous Byzantine systems that have rigorous math proofs of asynchronous Byzantine that are still practical? Sure. So if you'd like to see one, I'll show you one. This is Hashgraph. This is what we have. So first of all, the goal here is to be fast, right? Asynchronous Byzantine's easy. We've had this for 30 years. We know how to do it. But the systems that we've had for 30 years are so incredibly slow. To my knowledge, no one has ever deployed one of these voting systems in the wild. A pure voting system running one of these 30-year-old algorithms just isn't practical. So if we want real speed, how do we achieve it? All right, let's start by forgetting about consensus entirely. If we're talking about how fast a single shard is, a single replicated state machine, then all the nodes are going to have to get all the transactions. So just for that, that's the bare minimum we have to achieve, even before we start talking about consensus. What is the fastest way we could do it? Well, the fastest way would be something like a gossip protocol. This is the fastest, most resilient way we can do it. And all it says is it's the simplest imaginable thing. If Alice has a transaction she wants everyone to know about, she takes her red transaction there and sends it to a completely random person, Dave. And now, instead of one person knowing it, 2 people know it. And then each of them send it to a completely random person that they choose, and now 4 people know it. And then each of them send it to a completely random person, and now 8 people know it. And you keep going this way until everybody knows it. It is exponentially fast. You can say it's an expander graph, and it's even better than that in certain ways. It grows exponentially fast, how many people know it. If somebody attacks with that denial of service attack and shuts down one of our computers, we don't care. We're just constantly picking people at random. If I pick one that's down, then I'll just try somebody else. And my thing spreads out exponentially fast regardless. It is incredibly resilient. It is incredibly fast. It's used all through computer science for all sorts of things because it is so fast. So if we really want a fast system, we should start this way. Then the real question is, what happens if 2 people want to do a transaction at the same time? So what if Bob wants to do the green transaction there and Carol wants to create this blue transaction? What do we do? Well, we could have a leader. They could send it to a leader, and the leader puts them in order and sends it out to everybody. But that's a bottleneck. I want real speed. I don't want them to send it to a leader. Or they could take turns. Bob could send out his first, then when he's done, Alice could send out hers. Carol could send out hers. But that also is slow. Now Carol has to wait until Bob is done. Well, that's not good. What would be the fastest way to get it out? Just send it out. Each of them send it to some random person. Each of them now has 2 people knowing it. Then each of them send it to some random person. Each of them has 4, and then each of them has 8. It explodes outward exponentially fast until everybody has it. This is the fastest way we can get things out. Great. Only problem is there's no consensus here. Look at Alice. Her top one is a green one. Top one for Bob is blue. Everybody received them in a different order. What order should these be in? This is incredibly fast. In fact, this is the limit of speed for the internet, but we don't have consensus. All we did is got our transactions out. Well, that's no good. Let's continue to ignore consensus for just a second, and I'll point out something kind of surprising. If we add a tiny bit to each message, like make it 1% bigger, or even less than 1% bigger, just add a few bytes to each message, we can get, basically for free, an entire history of how we've all talked to each other. We can see exactly who talked to whom, in what order, exactly, almost for free. And then the fun thing is, after that, we can get consensus for free. No communication for consensus. And it's asynchronous Byzantine. That's the Hashgraph algorithm. So how does that work? Well, let's go back to the beginning. We did this gossip protocol. What is a gossip protocol? You know, we could draw a diagram of the history of a gossip protocol. Here's a diagram. Each of those circles is the event of somebody gossiping to somebody. Time goes uphill so that one at the top is Bob, it's in the Bob's column, being told everything that Carol knows because it has a diagonal line down to Carol. So that top circle is the event of Carol telling Bob everything she knows. By the way, in the protocol we just saw, you may have noticed sometimes somebody would actually pass two messages when they talk to somebody. The goal here in a gossip protocol is when I call you up, I tell you everything that I know that you don't know. And it turns out there's some really cool tricks we can do so I don't have to tell you stuff you already know. And we can very quickly figure out what you need to know. So that top circle means that Carol called Bob and told him everything she knows. And this diagram, you can actually follow exactly how things happened. If Alice knew stuff at the bottom there, she told Bob, and then a little while later, Bob told back to Alice, and Carol at the bottom told Bob, and then he told Carol. You can just trace through the diagram. You can see a complete history of how we all talk to each other. This is a gossip protocol. They're used all over the place. We can gossip about transactions, which is what we've been talking about. We can gossip about identities, which I think was the original use of the very first gossip protocol. We could gossip about databases. We could gossip about information. But what if we were to gossip about gossip? What if the thing that we're telling each other is this very picture? Very self-referential here. The picture of how we've all talked to each other is the thing that we were all talking to each other about. Or to put it another way, each of these circles is actually going to be a little data structure in the memory of my computer. And when I call you, I'm going to give you all the little circles I know, all these events. I'm going to give them to you, all the events that I know that you don't know. And then when you call someone else, you're going to give them all the events you know, including the ones I just gave you. So we're going to gossip these events. Now, once we have gossiped these events, because they have these lines connecting them, they actually give us this picture. We're all going to have the same picture. We're all going to know exactly what each other knew throughout history, which is so much information that Alice can say, you know what? I know what Bob knows. I know when he knew it. I know when he learned every single piece about this diagram in his whole history. If we were to run one of those 30-year-old Byzantine voting algorithms, I know exactly how Bob would vote. So he doesn't have to vote. I'll just pretend he sent me the vote. That's it. So what we're going to do is virtual voting. We do not have to send each other any votes at all, nor receipts on our votes. It's purely in your mind. But because we all have the same picture, we all have the same knowledge about the history of talking to each other, we will all come to the same conclusion. We're all running the same deterministic algorithm on the same graph. We all get the same answer. And you can mathematically prove, using proof techniques very similar to the stuff used 30 years ago, that this is asynchronous Byzantine. We will all come to the same answer. We will come to a conclusion, a consensus on whatever it is we're coming to a consensus to. And actually, what we'll do is we'll put transactions inside of these circles too. When I gossip to you, I'll actually send you some transactions also. And so what we really want to do is put all of these circles into an order. We want a total order on events. And we'll use one of the 30-year-old algorithms with some tweaks in order to do that. And we can come to a consensus on events extremely quickly with zero communication over the internet. In fact, what's in those circles? Well, one of those circles is like a block. It has whatever transactions you want to put into it. It has a timestamp, which is just one computer's opinion on when they created this event. It's digitally signed. All of that is what we'd have to do as the bare minimum just to get the information out about the events. And then we added just two things, two hashes. Each of the circles in that diagram has two lines coming down to previous ones. This is a directed acyclic graph. To turn it into a DAG, all you need are two arcs on each vertex, two edges on each vertex. Those are the two hashes. So we call this a hash graph. It's a graph held together with hashes. And the only information we're adding over that bare minimum to get the information, to get the transactions out, the only thing we're really adding are two hashes in each of these events. Oh, and by the way, those two hashes that I send you, when I send you an event, those two hashes are of two objects you already have in memory. You already know a short list of hashes, and you know it's two of those. So I don't even have to send you the whole hash. I can compress it down to just a byte or two, because you already have it in memory. I just have to remind you of which of the ones in memory I'm referring to. So we can compress even that down to almost nothing. So what we do is the fastest form of getting the transactions out that is allowed by the internet and the laws of nature. We add a tiny bit of extra information, which then gives us this entire hash graph, the entire history of how we all talk to each other, and then we get consensus for free. And it's asynchronous Byzantine, and we have detailed math proofs of all that. So that's kind of fun. It is possible to have consensus algorithms with mathematical proofs of asynchronous Byzantine, the very strongest kind, and they're very fast. And so we've seen hundreds of thousands per second. We've seen less than a second consensus time. And when we get consensus, you know you have consensus. You always reach a moment when you say, I absolutely know consensus, and I'll never be wrong as long as less than a third of us are evil. So I think that's kind of fun. Now the question is, what would you find entertaining at this point? I would find entertaining hearing a case study of just what were some of the attacks you were thinking about when you were building this. Or what are some of the attacks that we as a community can think about? And of course, over the last 2 days, you've heard of a million of them. So this is all review, but it's kind of fun to see a list of the sorts of attacks that we should be talking about. And part of the reason why I think it's important that we actually do math proofs of how secure we are is because there's an infinite space of attacks. And we're never going to think of all the attacks and make a list of all of them. We actually need to prove that our systems exclude all attacks or exclude huge classes of attacks that we can carefully and mathematically define. And so that's another reason I'm showing these attacks, is just kind of to say, you know, the space of attacks is really large. But of course, if you've been here for 2 days, you already know that because that's what everyone's been talking about, and it's been fascinating. I hope you've enjoyed this conference as much as I have. We have had some really good speakers. So when I was working on this, I thought about proof of work. There were several reasons that it wasn't as interesting. First of all, it's not Byzantine. Typically, the proof of work systems, there's never a moment when you know you have consensus. You just get more sure over time. And it's inefficient. I'm not particularly a fan of using a huge fraction of humanity's electricity and spending lots of money on these mining rigs. But I was also concerned about consolidation. If the mining rigs are expensive, then you might expect, if there's economies of scale, then you might expect that the number of miners would go down over time. If electricity is a big cost here, then you might imagine that you would have geographic concentration where all the miners move to where the electricity is cheap. And if you have miner consolidation and you have geographic consolidation, then perhaps that undermines the security of the system. And so maybe there's some self-defeating feedback cycles going on here. And I worried about that. What about geographic consolidation? What happens if everybody moves to one country and then the country nationalizes the mining rigs and sets them all to always extending the shortest path on a fork rather than the longest chain? Then it just kind of destroys the whole system. And would a state do that to destroy a cryptocurrency? Well, probably not, but you know, I don't really want to have to trust any one actor. I don't want to have to trust any one state not to destroy it. And so that's the concern. I want to have distributed trust. So I don't want geographic consolidation because then one state can nationalize all the mining rigs and cause them to attack our network. So those were some of the concerns. Also, people talk about 51%, although we've also had people say it correctly. You know, Bitcoin is a 34%, a one-third vulnerability. Turns out there's a math theorem, everybody's one-third vulnerable. There is no 51% vulnerable system out there. They're all one-third vulnerable. So some of the things I was worried about was, well, if we have a bunch of nodes, each of those computers is a computer, it's a full node, it's a miner. And what happens if we have geographic consolidation and maybe a country builds a firewall around them? What happens if they turn off the firewall? Could we get a different chain on the inside versus the outside? I don't know, maybe we could. Oh, we'll build a partition detector. Okay, what if they start flickering the firewall? Will that interact badly with our partition detector? I don't know. Or what if they start just delaying things? Delaying packets enough so maybe we start to have a difference of opinion on which chain is longest. Or maybe they do other malicious things. I started worrying about all those things. For example, what if those yellow nodes are compromised? A third of our computers are bad, or in this case, a third of our hashing power is bad. And we have a firewall, and the firewall is colluding with the one-third. You could imagine on any given yes-no question, like, we have a fork of these two chains. Should I extend this one? Is this the longer one? Any yes-no question. You could imagine that the honest nodes outside the firewall happen to vote yes. The honest nodes inside the firewall happen to vote no. And the dishonest nodes are duplicitous and vote no to the guys inside and yes to the ones outside. And they're actually going through the firewall because they're colluding. And now we have a real fork. The people inside think that 2/3 of us are saying no, and the people outside think that 2/3 of us are saying yes. This is a problem that destroys it. You end up with a false consensus with only a third of us being compromised. Now, that attack doesn't really bother me because every system has that attack. And I'm only putting it up here because it was one of the things I was thinking about. We have a decades-old theorem that says every system is vulnerable to one-third. The proof of that theorem is basically that picture. That's the proof of the theorem. That's a math proof. But it's interesting to know. We just need to be clear as a community on what our security is, and none of us are more secure than 1/3 of the influence. So if you use hashing, it's 1/3 of the hashing power. If you count IP addresses, it's 1/3 of the computers. If you do proof of stake, it's 1/3 of the coins, or 1/3 of the stake. But nothing can survive a third being compromised, and this is why, assuming the bad guys have the ability to do things like firewalls. So I'm just telling you some of the things I was thinking about. We as a community, are talking about these things, which is good. Now, leader-based is not quite 30 years old, although it's pretty close. And so you have PBFT and Paxos and Raft and all these leader-based systems that you may be familiar with. The idea is really simple. Everybody sends their transactions to the leader. The leader gets to pick the order, tells everybody what the order is, and we all agree. And maybe we send signed receipts back. Beautiful. And maybe the leader eventually crashes and we have to elect a new leader, and then the algorithms are really complicated to do that, but they work it out in a Byzantine way. Beautiful. I love it. Now, you don't get fairness. We haven't really talked about fairness, and I'm not really going to talk about fairness very much, but it's not fair because the leader can put them in any order they want or even leave out one if they want to. The Hashgraph algorithm, by the way, we have a math proof that it's fair. But that's fairness. So what happens with leader-based? If Alice is the leader, here's a problem in addition to fairness, is the DDoS attack. What happens if Bob is malicious or has a virus on his computer? And he directs a botnet, a bunch of compromised computers, out on the internet, and they all attack Alice, shutting her down. Then we're all shut down. And by the way, this might not be a traditional leader-based system. This might be a leader-based system where we change leaders every 2 seconds. Wonderful. They only shut us down for 2 seconds, right? Or maybe it's a traditional one, but maybe after 15 seconds, we all get tired and elect a new leader. Great, then they only shut us down for 15 seconds. Or maybe this is two-phase commit in a database. Two-phase commit with locks is actually another form of leader. Whoever's holding the lock is the leader. But maybe eventually we decide, oh, whoever was holding the lock crashed, and we claw back the lock and give it to somebody else. There's lots of things we can do, but Bob has an infection or is malicious, and he can say that when we elect Carol as our new leader, before she gets to do anything as a new leader, he redirects the botnet against her. And so we can shut it down forever. So even if we're doing a round robin where we have a new leader every 2 seconds, a botnet can shut us down forever, only shutting down one computer at a time. Very fragile. This is why I didn't really want to go down the route of leader-based. I really wanted this to be more everybody's equal at every moment. And many, many systems you wouldn't think are leader-based, like a system where we're all going to vote, but one person has to propose the order, has to propose the next block. I don't know, is that proposer a leader now? There's a lot of hidden leaders in a lot of systems, and maybe they're vulnerable to this. Plus, they're always vulnerable to the fairness problem. I also looked at some of the economy things. There's a lot of different ways of doing this. You could talk about something like a simple system where we all bet on which of two chains is longer. And then the people who bet the same way get money, and the people who bet the wrong way lose money. Then we have an economic incentive to all agree with each other. Are there any problems with that? Sure. What happens if there's a firewall? Do we end up getting partitioned? I don't know. Do we have firewall detectors? Do they interact badly? I don't know. Or what if the firewall is just delaying messages so we have a different opinion of what's the longest thing? Is that going to hurt us? I don't know. What if it's, and it's certainly not going to be Byzantine in this kind of a situation because we're going to have these two forks that take a while to resolve themselves. And then what if we're infected? What if we just have a tiny number of computers with a tiny amount of hashing power and a tiny amount of stake, the red ones there that are infected, but half of them send a yes to half of the population and half send a no to the other half of the population, where we're voting on some yes-no question, and they happen to be really fast. Maybe they even use a botnet to talk faster, or maybe they just have fast internet connections. You could imagine people being tricked to vote for the wrong thing. We end up having half of us voting for the wrong thing, and so half of us lose money. If we do this a bunch of times, all the honest people start saying, you know what? I'm not going to vote until I see enough other people voting. I'm not going to go first. Well, if all the honest people just say I'm never going to go first, then nobody ever goes first and the entire network freezes forever. So these are the sorts of things I was going through. There's a million ways of fixing that, and then ways to attack the fix, and then ways to try to fix the attack on the fix, and then ways to attack the fix on the attack on the fix, whatever. I was never able to prove true asynchronous Byzantine in the strongest sense for one of these systems. And if we have some of these systems that really are asynchronous Byzantine, we need to take the time to prove it. So what would I say? It's great that we're building systems that have no proof at all for security, but I think we're getting to the point where we need to start having proofs. So anything is better than no proof. If you can do partially asynchronous Byzantine, that's better than no proof. Do that. Take the time to do that proof. If you can, though, compromise on the Byzantine half instead of on the asynchronous half, and do asynchronous partially Byzantine, honestly, that's better. And then, of course, if you're able to prove asynchronous Byzantine, well, that would be best. So do that. And it's not on the slide, but if you can prove fairness, hey, that's gravy. That's even better. So that's all I have. I hope it was entertaining. And thank you for your attention. I have a couple minutes for questions. Oh, yeah, right. I love this microphone. I would rather know that a system is somewhat secure in exactly what way it's insecure in this world than to know that it's totally secure in a fantasy world. So if you believe that botnets exist, I really want your assumptions to say there are botnets in the world. That's why. Oh, and I didn't repeat the question. The question was, why is compromising on the Byzantine part better than compromising on the asynchronous part? That's why. Yes. I'm sorry, you have a, yes.
Sorry. Thank you so much for your talk. I was hoping you could expand on the modeling of honest versus malicious nodes, because to me that seems to be an assumption that doesn't necessarily match the real life scenario. Like, you might have people, like everyone might be majority honest most of the time, but they might want to cut corners sometimes. So are there any alternative models to the honest versus malicious dichotomy?
Yeah, so the short answer is nope, this is the terms that says this is the best you can do. But of course, honest here doesn't really mean honest. Malicious doesn't really mean malicious. There's lots of caveats on what exactly we're talking about. What we have is we want people to be following the protocol, and we can incentivize people, and half the talks this week have been great about how do you incentivize people to follow the protocol. We can punish people for not following the protocol, but ultimately, we have to engineer a system where at any given moment, more than 2/3 of us are following the protocol. Because if a third or more of us are willing to violate the protocol and do arbitrarily bad things, you are sunk, and that's a math theorem. And so that's a fact of life. And so That actually implies that crypto economics would be important. We ought to have a conference on that. That's a good subject. One last question.
Oh, gosh.
Two last questions.
You say asynchronous here. Do you mean partially synchronous? Because isn't the whole point of the FLP theorem that like you can't get asynchrony in like you can't get Byzantine fault tolerance, like both consistency and availability, like in
No. FLP says you can't do it without randomness. So you use the random number generator in your computer and you can do it with probability 1. FLP is an impossibilities theorem for deterministic algorithms, not for non-deterministic. So if you use random numbers, you're fine. And then you don't get guaranteed, you get guaranteed with probability 1.
Okay.
Yeah, it's a common misconception about FLP.
Right.
There was an earlier speaker who actually said it correctly, that FLP is impossible unless you use entropy.
Right.
Right.
Okay, sure. And then the other question I had was for the in the DAG that you have of messages,
Yes.
right? If you have a double spend on two different blocks that are you can't order them, do you have some sort of heuristic for deciding ordering between those two different blocks?
I apologize. The whole point of the Byzantine stuff was to put all those circles in a total order. So we get a total order on all those circles, guaranteed with probability 1, as long as less than a third of us are bad. The whole point of this was to put it in a total order. I didn't give you the actual algorithm, but it's the old 30-year-old algorithms, basically. But we get a total order. And so, yes, we do. It's not one of these partial order things. It's a total order. The DAG gives you a partial order, but we extend that to a total order. That's a really good question. I apologize that wasn't clear, because that's the whole point of the system.
Okay. Cool.
Yeah, very good. Thank you for that question.
Sure. Thank you very much.
Thank you.